Welcome to Chemistry 30 Prep, Unit 1, the diversity of matter and chemical bonding. This lecture we're going to be covering some of the basics about the atom and the periodic table. In your textbook it is pages 1 to 7 in your Inquiry into Chemistry. The objectives of this lecture: by the end of this lecture you will be able to describe the quantum theory of the atom, describe the differences between atoms, elements, and isotopes, use the periodic table to classify metals, nonmetals, and metalloids, and you will also be able to identify empirical properties of metals, nonmetals, and metalloid elements. The quantum theory of the atom is the current theory of the atom that's used today. It suggests that atoms are tiny positively charged spheres consisting of two types of particles: protons that provide the positive charge and neutrons which provide no charge. Surrounding this tiny sphere is a cloud of negatively charged particles. These negatively charged particles are called electrons, and electrons are much smaller than protons. The charge of a proton is equal in magnitude to the charge on one electron. So even though there's a size difference between the two, they both carry the same amount of charge, but with opposite amounts. So the net charge of an atom is always going to be zero because atoms have an equal number of protons and electrons. For every positive charge in the center of the atom, there is a negative charge in that cloud around the atom. Now, elements. A group of identical atoms is an element. So atoms that have the same number of protons all have the same chemical properties, and it's the number of protons in the nucleus of an atom that determines its chemical properties. So two atoms that differ in the number of protons will be separate elements. So for example, helium gas consists of two protons in its nucleus, and one of its physical properties is that it's a gas at room temperature. It vaporizes at minus 269 degrees Celsius, and so this is the helium gas that you would use to fill up helium balloons, the balloons that float at birthday parties. If we compare that to lithium, lithium is an atom that consists of three protons in its nucleus. It's a solid at room temperature, and it vaporizes, or it turns into a gas, at 1342 degrees Celsius. So even though the two of them only differ by one proton, they have very different physical properties and very different chemical properties as well. Isotopes are two atoms that differ in the number of neutrons inside the nucleus of the atom. So the elements will be of slightly different masses. Since the number of protons are the same, isotopes are still the same element and have the same physical and chemical properties. So the number of neutrons has little effect on the element's physical and chemical properties. An example would be carbon-12 and carbon-14. Both of these atoms are carbon, so both of them will have 6 protons, and both of them will have 6 electrons. On Earth, over 99% of carbon atoms on Earth have 6 neutrons. These will be carbon-12 atoms. They have 6 protons, 6 neutrons, so this would be carbon-12. About 1% of the carbon atoms on Earth have about 8 neutrons, so about 1% of the carbon atoms on Earth have 2 extra neutrons. This would be your carbon-14. They would still have 6 protons and 6 electrons, but the heavier carbons have 2 extra neutrons. So both of these isotopes are isotopes of carbon. They are found in living organisms, and they both have basically the same physical properties. One atom of carbon-14 is slightly heavier than one atom of carbon-12. When we're representing atoms or representing elements in isotopes, in chemistry we use shorthand notation that follows this basic format. And what this does is it allows us to communicate elements in a more timely fashion and with a little less writing. So they provide a summary of the atom's composition, and it consists of 3 parts. The first part is the atomic symbol. So the atomic symbol in this case would be where this giant X is. So this here is your atomic symbol. It is a 1 or 2 letter symbol that lets us know what element from the periodic table we're talking about. The next component is the mass number. It's the number of protons and the number of neutrons added together found in one atom of the element, and that's where this A is here. So the superscript is the mass number, the subscript is the atomic number, so the Z would be the atomic number. It lets you know how many protons are inside the nucleus, and it's unique for each element. So what this means is for every element, the number where Z is and the symbol where X is will always coincide, or they'll always be the same, and I'll show you what I mean. If we look at the element iron 56, so this 56 tells us the atomic mass of our element. So it's the mass of one atom, so it's 56, and it's equal to the number of protons plus the number of neutrons inside one element or one atom of this element. So the atomic symbol is Fe. For iron, the atomic symbol is always Fe. The number of protons is 26, and iron always has 26 protons. You can get this off of our periodic table, and we'll take a look at that in a little while. So what that means for our atomic symbol, the number 26, if it's in the proton spot, and the symbol Fe always go together because iron always has 26 protons. The number of neutrons in this atom is 30, and it would be the atomic mass, which is 56, minus the atomic number, 26, and this is going to give us the number of neutrons. And so this is what the atomic symbol would look like. The 56 is the superscript, the 26 is a subscript, and the Fe is the atomic symbol. When we compare isotopes, there's a couple of things we have to keep in mind. Here are three atoms, and they differ in either their atomic mass or their atomic number. Now, if we take a look at the first two, the carbons, each of these big C's is the symbol for carbon, so both of these symbols here are carbon atoms. Because they're carbon atoms, they will always have 6 protons. And we can see that here. 6 protons, 6 protons, that means it's carbon. The difference here is in the mass number. Now remember, the mass number is the number of protons plus the number of neutrons. So what that means is, for carbon 12, we know that there's 12 is equal to number of protons plus the number of neutrons, which would be 6 plus, in the case of carbon 12, it would have to be 6. That's where we get our 12 from. So carbon 12 has 2 less neutrons than carbon 14. They have the same number of protons, but carbon 12 is a little bit lighter. It has two less neutrons. When we take a look at carbon 14 and nitrogen 14, N is the chemical symbol for nitrogen, so we know this is a nitrogen atom, and nitrogen always has 7 protons. So these two things always go together. The 7 in the atomic number spot and the atomic symbol N always travel together. This 14 is its atomic mass. So when we compare it, so it's completely different from carbon 12. They have different atomic masses, they have different atomic numbers, They're completely different elements. If we take a look at carbon-14 and nitrogen-14, we see they both have the same atomic mass. So both the carbon-14 and nitrogen-14 have same atomic mass. They have a different number of neutrons, or protons I should say, so they differ in the number of protons. Which is the 6 and the 7. So nitrogen has one more proton. They also differ in the number of neutrons. Carbon-14 has, as we said before, 2 more than carbon-12, so it has 8 neutrons. Nitrogen, I'll just write it down here, has only 7 neutrons, because it would be 14, the atomic mass minus 7 is equal to 7 neutrons. So those two elements are actually quite different. Even though they have the same mass, they differ in both the number of protons and number of neutrons. So the periodic table is where we're going to find all of our elements. The periodic table is a systematic arrangement of atoms based on their similarities and differences to and from each other. So atoms are arranged horizontally according to increasing atomic numbers. So they're arranged by protons. The atom with the fewest number of protons is in the top right, hydrogen, and the atom with the most amount of protons is in the bottom left. Each horizontal row is called a period. Each vertical column ends up having elements that share similar chemical properties. And so each of these vertical columns is called a group. So periodic table, because the period is periodicity, a repeating pattern, and what that means is at a certain point atoms share physical properties, and it happens in a periodic way, or in a fashion that after about every 8 atoms or so, 8 to 10 atoms, we end up with atoms that have similar chemical properties. So here, this would be group. Groups go down, and each of these groups have similar chemical properties. Periods go across. And they're arranged just in order of protons. So hydrogen, the first element, has 1 proton. Helium, the second element, has 2 protons. And notice that helium is over top of the first group because it shares chemical similarities with the first group. And hydrogen per se, helium is over top of the last group, group 18, because it shares chemical similarities with the atoms in that group. And then after that, the table gets a little bit more regular, and we'll talk more about what some of those chemical properties that each of these groups has. When you're looking at the periodic table, there's a key for each element. Each element has certain information displayed in the periodic table that describe it. So the first number is the atomic number. This is the number of protons. You find that in the top left. Other things that we're going to know is, notice that the atomic mass, or the atomic molar mass, very similar to atomic mass. When you round this number, you get your atomic mass. So in this case for iron, this is describing iron. Most iron has an atomic mass of 56. We'll be talking about these ion charges a little bit later. Notice the boiling point and melting points are listed for each element. Electronegativity we're going to be talking about, and then the symbol and the name. When you take a look at the symbol, you can tell the state at room temperature, so whether or not it's a solid, a liquid, or a gas. In this case, the element is a solid because the text is a normal text. Liquid elements have italicized text, and gas elements have shadowed text or hollow text. Elements that are found in nature have black writing. Elements that are synthetic or can only be created in the lab have green writing. So if we just go back to our periodic table here, we can see just by looking at some of these elements, we can see that most of the elements are solids. Most of them have normal writing, especially when we look on the left-hand side. Other things we notice, so if we take a look at, where's my pen here? This element here is a synthetic element because it has green writing. Here we have an element that's liquid at room temperature. This is mercury because of the italicized writing. And here, these are hollow ones. So these would be your gases. So just by looking at the symbol, we can tell the state of an element. So here we're taking a look at the bromine atom, just as an example. The number of protons for this bromine atom would be 35. And that we just get from this corner here. For the number of neutrons, we have to do a little bit of math. We take the 79.90, round it off to 80, and then we take that 80 and we subtract the number of protons in the element, and we get 80 minus 35, so that's going to be 45 neutrons. The boiling point would be 59 degrees Celsius. And its state at SATP, we take a look at the symbol, we see that it's italicized, so we know that it's a liquid. When you look at the periodic table, they are arranged into groups, and each group is named based on the properties that it has. So if we take a look at the types of elements, there's a couple of things we need to take a look at. The first thing we're going to take a look at is this staircase here. This dark or this bold line separates the elements into two basic groups. The metals that are on the right-hand side, so they're in this bluey green, and the non-metals that are yellow. So if you're on the left-hand side of the staircase, you're a metal element. If you're on the right-hand side of the staircase, you're a non-metal element. With one small exception, you'll notice there's a set of green elements that touch the staircase. These are metalloids. And each of these three groups has different physical properties that help define what it is. So everything on one side has a set of physical properties. Everything on the other side of that line has a different set of physical properties, and that's one of the ways they're grouped. Some of the group names that you should know are on this table as well. The alkali metals are group 1. The alkaline earth metals are group 2. In the middle of that periodic table, we have transition metals, which are groups 3 to 12. And then the other names you should know would be, for groups 17 and 18, halogens and noble gases, respectively. The lanthanides and the actinides, those inner transition metals, on the periodic table, they're not special so much as we need to save space. So where they actually belong is right here, in these two rows here. So if you were to stretch the periodic table out by inserting these two rows, you'd have a very long, narrow periodic table, which would be hard to put on a piece of paper. So what they've done is they've just taken out those two rows and placed them at the bottom of the periodic table. So metals and nonmetals. All of those metals in physical appearance are shiny and bendable. They are all good conductors of electricity, and all except mercury are solid at room temperature. Most elements are metals. If you take a look at your periodic table, you'll see that almost 2/3 or even 3/4 of those atoms are on the left-hand side of the periodic table. Nonmetals, on the other hand, they're not shiny or bendable. They do not conduct electricity or heat in their solid forms, so they're good insulators, and most of them at room temperature are gases. In their solid forms, they're usually brittle as opposed to being bendable or ductile. The last group is the metalloids, and it's a group of elements that don't fit either the definition for a metal or a non-metal. Some of them are shiny, some of them are dull. Some conduct electricity, others do not. All of them are brittle and not very ductile. So these are the metalloids, and they are they're the green ones that touch the staircase on the periodic table. So those about 7 elements, you can just take a look at that. 1, 2, 3, 4, 5, 6, 7, 8 elements are metalloids. And they have some of the properties from either group. So some of the properties of the named groups that you should know are the group 1 metals. They're extremely reactive with water and oxygen, usually producing flames when mixed with water or oxygen. They're soft and they're shiny in their pure forms, which we never see in nature. In their pure form, they don't exist in nature. They're always in compounds. They react with halogens, so the group 17 elements, to form common chemicals such as table salt and rock salt. The alkaline earth metals are also a very reactive group. Very rarely are they ever found in their pure form. They're usually in compounds, especially reactive with oxygen. So there's lots of oxygen around, so if they're exposed to the open air, they're going to be reacting with oxygen. And they react in a 1-to-1 ratio, or 1 atom of a group 2 metal reacts with 1 atom of oxygen at a time, or equally. The halogens, the group 17s, are extremely reactive, and they react with water to form acidic solutions. And the noble gases, what makes them special? The 3 groups we've talked about ahead of them are all very, very reactive. The group 18, or the noble gases, are almost completely unreactive with other elements. In nature, they're never found in compounds. They're only found in their pure form. And so these elements were looked at to see, well, what makes them so special? And it turns out that they're of special significance to chemical theory. And it has to do with valence shell of their valence shell of electrons is full, and we'll talk about what a valence shell is in tomorrow's lecture. So for homework, just read through the first 7 pages of the textbook and try the Q questions number 1 and 2. The answers for these questions will be posted on the website.